Hey there, in this video we're going to continue our discussion of center of mass from section 8.3. So we're going to do another example to kind of follow along what we did in class. So in here we want to find the center of mass of the thin plate of constant density. The plate is formed by the region in the first quadrant bounded by these functions. So we have the y-axis, the parabola y equals 3 minus x squared, and the line y equals 2x. So I outlining the region here. So R is where we want to find the center of mass. So this is not a symmetric region, so we want to figure out, well, where is the balancing point? And so we need to find the centroid, which is the notation x bar, y bar. And so just to remind ourselves the formulas, so x bar is where is it going to balance along the x-axis so that this doesn't have a tendency to rotate towards the y-axis. So think of it as like a door. So what is going to keep it open, not wanting to turn towards the y-axis. So our x bar is the moment about the y, so that's why it's the moment about the y-axis, that tendency to want to rotate towards the y-axis divided by the total mass. So to break this down a little bit further, what we did in class is we said this is the integral from a to b of the density times the distance to the y-axis times the area. So density times area times distance to the y-axis. So the distance, so if I put our little sample strip here, and so we want to put the center of mass of that one. So this is going to be our little sample one. So then what is that distance to the y-axis? So the distance to the y-axis is x, right? You're at a random distance of x away from the y-axis. So we'll call that x. So the distance to the y-axis is x times the area of this little rectangle. So the area is top minus bottom, right? So f of x minus g of x dx, because this is our little dx. And the total mass is the density times area. So the integral from a to b of density times the area, which is just going to be f of x minus g of x dx. In this particular case, we're told that the density is constant. Right? We're told here constant density. So notice that because the density is constant here, when you take it out of the integral as a constant, they're just going to cancel out. But that's the only thing that cancels out because it's a constant. If it wasn't constant, we can't cancel it. So I'll do the same example, the same region, but with density that is not constant. And so similarly, y bar, the place where it balances along the y-axis, right, where along the y-axis from 0 to 3 is this rectangle going to balance, this region going to balance. So where along the y-axis or y-coordinate of the centroid will it keep from rotating towards the x-axis? So then this is the moment about the x, right, the tendency to rotate towards the x-axis divided by the total mass. The total mass is the same, so we just need to figure out the moment about the y. And as we talked about in class, this is the density times, we found the distance to the x-axis a little different by doing the average. And so you can look at the notes from class or the comfort zone video on how we got that. But then what we ended up getting was 1/2 f of x squared minus g of x squared dx. And this was to keep it as a dx integral. We could also write it as a dy integral by saying the distance to the x-axis is y, and then doing right minus left to find the area. But that would be as a dy integral. I want to keep everything dx. And then density times area, the regular mass. Again, density is constant, so here we can cancel it. just because it's constant, right? If density is variable, we can't do that. So one of the first things then, notice that both of them require the total mass. So one of the first things that I usually do is find what the total mass is. So because density is constant, I don't need it. So the total mass is the integral from A to B of just the top minus bottom. Just as we did finding the area between two curves at the beginning of the semester. Okay, so I need to set up this integral for this region. So I need to figure out what are the points of intersection. So we need to figure that out. So where do these two functions intersect? So we want 3 minus x squared, the parabola, to be equal to 2x, right, to find the intersection points. And solve for x. So I'm going to set it as a quadratic, so set it equal to 0. So I'm going to have x squared plus 2x minus 3. And hopefully that factors, and it looks like it does. Two numbers are multiplied in -3 and add up to positive 2. That will be x plus 3 and x minus 1. So that means that x is equal to 3. Oops, sorry, -3, or x is equal to 1. We're in the first quadrant, so x equals 1 is the one that works for us. So when x is 1, what is the y value? So our intersection point is 1, comma, this was the line y equals 2x. So when x is 1, 2 times 1 is 2. Or you can put it into the other one, right? This one was y equals 3 minus x squared. So when x is 1, 3 minus 1 squared is 2. So they intersect at the point 1, 2. I guess we don't need the y value. Unless you're doing the moment about the x as a dy integral, then your integral will go, you will need that. But notice that you will need two integrals there. Okay, so let's move on. So the total mass, now that I know the intersection point, I can say is the integral from 0 to 1 of the top function minus the bottom function. So the parabola minus the line. So 3 minus x squared minus 2x dx. And then we integrate from here. So I'm going to have 3x minus x cubed over 3 minus x squared from 0 to 1. And so when you plug in 1 and 0, you're going to get 3 minus 1/3 minus 1. Make sure I've done this correctly. Which the common denominator is 3. So we can put that as 9/3 minus 1/3 minus 3/3. So it gives us 5/3. So that is the total mass. So now that we have this, we can go find the rest of the stuff. So our total mass, let's keep it as 5/3. And so for x bar, I know this is my over the total mass, so it'll be over 5/3. And y bar is the moment about the x over the total mass, which will be 5/3. So let's find the moments. So the moment about the y, right, the tendency to rotate towards the y-axis is the integral from a to b of density. In this case, density is constant, so we don't need it, of distance to the y-axis, which is x times the area. So top minus bottom dx. And the moment about the x is the tendency to rotate towards the x-axis. So that's the integral from 0 to 1 of 1/2 f of x squared minus g of x squared. So we found this formula. We did it in class. So if you are not sure where this comes from, go back and look at the Comfort Zoom recording for Thursday's class. Okay, so let's find the moment about the y first so that we are able to find x bar. So my is the integral from 0 to 1 of x times f of x minus g of x. So 3 minus x squared, the top function, minus the bottom function, dx, and distribute that x in. So we get the integral from 0 to 1 of 3x minus x cubed minus 2x squared dx. And now we can integrate this, and when you integrate this, you're going to get 7/12. So I kind of did the work over here, but make sure that you do the integral on your own and you'll get 7/12. So that's the moment about the y. So that means that x bar is my over the total mass, which now we know both. So the moment about the y, right, that tendency to rotate about the y-axis is 7/12 divided by the total mass, which is, what did we get, 5/3. So simplify this. So 7/12 divided by 5/3 is the same thing as multiplying by 3/5, the reciprocal. So we get 7/20. So that is x bar. So this is the x coordinate of the centroid, of the center of mass. So that means, going back to our picture, that if we are, so we're between 0 and 1, so 7/20 is, make sure first of all that it is between 0 and 1, so and it is 0.35. So our center of mass along the x-axis, so here's 0.5, and so 0.35 will be, so there's 0.4, 0.3, 0.2, 0.1, and so on. So it'll be somewhere along here. So that means that it will balance at 0.35, and now we need to figure out where along the y-axis is the other balance point for our centroid. So now we know that x bar is 7/20, so what's y bar? And then we'll know exactly where the center of mass for this thin plate that has that shape is. So let's now use the formula for mx. So we have y bar. Y bar is the moment about the x, a tendency to rotate towards the x-axis divided by the total mass, which is 5/3. So let's use this formula for mx. So mx is the integral from 0 to 1, right? I'm keeping it as a dx integral of 1/2 times the top function square, so 3 minus x squared minus the bottom function square, dx. Now I could change it to a dy integral and say then the distance to the x-axis, which will be y, times, and then the area, which will be, as a dy integral, you have to do right minus left, but notice that right minus left means you will have two integrals, one from 0 to 2, and then from 2 to 3. So it's better to do it as a dx integral anyway. Okay, so let's work this out. So I'm going to take the 1/2 out. So 0 to 1, square this out. So we're going to get, what's that, 9 minus 6x squared plus x to the 4th minus, notice that the minus here, that's just our subtraction. We're not squaring that negative. We're squaring just the 2x. So 4x squared. dx, we can't combine like terms here. So this is 1/2 the integral from 0 to 1 of 9 minus 10x squared plus x to the 4th. And so go ahead and solve this integral, and what we'll get is 44/15 after you complete the integral. So go ahead and make sure that you do the integral on your own and make sure that you get 44/15. So now we can complete our y bar. So the y coordinate of the center of mass. So this is the tendency to rotate about the x-axis divided by the total mass. So the sum of the moments. And so this is 44/15 divided by the total mass, which we got 5/3. So 44/15 times 3/5. And simplifying this, what do we get? 44/25, which is approximately 1.76. So make sure that that is within our region. So the y bar is 1.76. So the y coordinate of the center of mass, which makes sense. Notice that our y goes from 0 to 3. So 1.76 is just a little bit before 2. So now we know that this is 1.76. So our center of mass, now you can put it in there. So 7/20 and 1.76. And what did we say that was? 0.35 and 1.76, and so that makes sense. That is within our region, and so that makes sense. Now, there are some objects, right, that whose center of mass is outside the region. So if things are not convex, and so like a boomerang, right, the center of mass is outside of the boomerang. And what other things? Can you think of other things that have the center of mass outside of them? I know even as a person, right, if your center of mass changes. If you lift up your arms, you're changing your center of mass. When you sit down, you're changing your center of mass. If you bend forward, your center of mass is actually outside of your body. And so those are things. So there are objects where the center of mass is not going to be inside of the object, but in a region like this, we should expect it to be within the region itself. Okay, so that is how you find the center of mass. So in the center of mass, is called the centroid. And so our centroid here is, what was it, 7 over 20, comma, 44 over 25. I prefer fraction forms, but if you want to put it in decimal, it will be 0.35, I think it was, and 1.76. So be mindful though of how many decimal places you're given. And so if you're putting your answers in WebAssign as decimal, just pay attention. Do they ask you to round to a particular decimal? And then make sure that you enter the answer that way. For me, during quizzes and exams, I prefer fractions. They're just easier to look at and to grade. Okay, so let's try, what about the same region, but what if, so same region with variable density. So say the density of the plate is given by x squared. So that means that the plate, as you get further along on the x-axis, the plate gets heavier. So x squared, right? So if you're over here, where are we? So at 0.5, the density, if you're at 1/2, the density will be 1/4, right? 1/2 square. If you're at 1, the density is 1 square, which will be 1. So it gets heavier as the closer you get to where the graphs intersect. So how does that change the center of mass? Right? What do you think is going to happen to our original center of mass, 0.35, 1.76? So this will be something to kind of think about. And so how does everything else change? Well, now we have density that's variable. So when we find the total mass, we say that this is the integral of from a to b of the density times the area. And the area is your top minus bottom. Now, if you only have one function, then it will just be your f of x. So in this particular case, it's going to be the integral from 0 to 1 of x squared, the density, times your top minus bottom. So 3 minus x squared minus 2x dx. And when you find this, we get the integral from 0 to 1, 3x squared minus x to the 4th minus 2x cubed. Sorry, things are not in decreasing order from degree. So as you integrate this, as you solve it, what you should get is 3/10 for the total mass. So now compare that to what we got before, right? Before we got 5/3 for the total mass. Now the total mass is 3/10. So that is changing because of our density. So the density changed, so that means that the mass is changing as you move along the interval from 0 to 1. And so as you go through this, right, I encourage you, so I'm going to have you do this on your own. Find x bar y bar for with density, the same exact region, so but with density rho equals x squared. And so that means, for example, what will your moment about the y-axis look like? So this will be the integral from 0 to 1. Now density is not constant, so I have to include it in there. So it'll be x squared times the distance to the x-axis, distance to the y-axis, which is x, times f of x minus g of x dx. So this is your 3 minus x squared minus 2x. So when you integrate this, what do you end up getting? For your moment about the x is the same thing, right? Integral from 0 to 1 of, and we're going to include the density now, times 1/2, and I'm going to do f of x squared minus g of x squared dx. So do that integral, and what do you end up with? And so what you should get in the end is that our centroid for density x squared is going to be 11/18, 40 over 21. So notice how the centroid changed from constant density to variable density. So I encourage you to do these integrals and make sure that you get this as the proper answer. All right, email me if you have any questions.